Okay, so in today's lab session, we'll just be going over the exam one that we just finished this past weekend. We'll be discussing each question in the exam, and if you have any questions or any part that I can address, don't be shy to ask verbally or in the chat. Okay, so let's look at this first question. So we're asked to show all major resonance structures. A main issue that I saw in the exam is students were drawing minor structures that weren't substantial contributors. We're asked to use arrow pushing notation to show the movement of electrons, and we're supposed to place a box around each resonance form that's the largest contributing structure. And then we have to label all carbons that have a partial negative charge and all nucleophilic carbons. So using arrow pushing notation, we can kick our lone pair through our pi system. And I explicitly asked you to draw each of the major resonance structures. So I notice on the exam, some students decided to skip some steps. Please make sure to draw out all of the major resonance structures. So let's do just that. Okay, so we're continuing to push our electrons throughout our pi system. And continuing on, we end up with a total of 5 structures. So if you had less than 5 structures, points were deducted. So this last structure at the bottom was considered the major structure, as it places its negative formal charges on the most electronegative atoms. Okay, in terms of assigning nucleophilic carbons, or carbons with a substantial partial negative charge, so we see in the following structure, each of our positions where we have a large amount of electron density in one or more of our major contributing resonance structures would be considered a nucleophilic carbon. So we have a total of 5 nucleophilic carbons in total for each of the 5 sites which have an excess of electron density in one or more of our contributing resonance structures. And with that, we've completed this question. Any questions on this example? Any questions on this example? Any questions that I can address?
Not for me.
Okay then, so let's keep going then. So in this case, we're asked to circle and name each functional group. Remember, you name each functional group as a whole. Don't break down an ester into the component ketone. This whole functional group is an ester. Some students miss this functional group, which is a thioether. This functional group is a carboxylic acid. This functional group is an amide. We have an amine. we have an aryl group, and we have an alcohol. Okay, next we're asked to label all sp2 and sp hybridized atoms. Any atom with a lone pair adjacent to a pi system will be sp2-like in character. So let's label all of our sp2 atoms, not just carbons, but sp2 atoms. I noticed on the exam, some students mark the amine and thioether as sp2, but the lone pairs aren't conjugated. And as a result, the amine and thioether prefer to adopt an sp3 hybridization. There's no delocalization of this lone pair and no stabilization of this lone pair via resonance. So there's no reason for the amine and thiol to adopt an sp2 configuration or hybridization. Okay, so we've labeled our functional groups, we've labeled our sp2 hybridized atoms, and counting them up, we have 7, 10, 13, 16. So we'd say that there are 16 sp2 atoms. And if we're asked to label the most acidic proton, the most acidic proton would be our carboxylic acid proton with a pKa of around 4. Does this example make sense to everyone? Does this example make sense? Okay, so let's keep going now. So we're asked to rank the following molecules in order of increasing acidity. If we think about conjugate base stability, we know that sp hybridized or sp orbitals are more effectively able to stabilize an anion compared to an sp2 or an sp3 orbital. As a result, because the sp hybridized atom and sp orbitals are more effectively able to stabilize the negative charge in our conjugate base, our alkyne for our sp hybridized carbon, which has a carbon-hydrogen bond, would be the most acidic carbon-hydrogen bond because the conjugate base is the most stable. Following that same logic, the alkene would be the next most acidic, while our alkane is the least acidic. Does this make sense? The alkyne is the most acidic. You don't actually need to explicitly know the pKa values. If you know the qualitative rules, you can get this general hierarchy. Looking at this next example, an aldehyde has a pKa of around 19 to 20, while a ketone has a pKa of around 22. So our aldehydes are most acidic, followed by our ketone. An ester has a pKa of approximately 30, while an amide has a pKa of about 33 to 35. So it would be our least acidic. Does this example make sense? You can also reason it based on donor capacity, and nitrogen is the most effective donor. And as a result, the nitrogen in the amide heavily destabilizes our conjugate base anion.
Can you just clarify on the ketone versus the aldehyde? So what are the different effects between the two? Because I thought because the the methyl groups on the end would have more of a like inductive effect, or
so the methyl groups are So the methyl groups are considered inductive donors. And as a result, they destabilize the conjugate base anion.
Oh, okay. Never
Yeah.
mind.
Well,
Okay.
if you compare that to an aldehyde, a hydrogen is a less effective donor because it's less electron rich overall.
Oh, okay. I flipped it. Okay. Thank you.
Mm-hmm. No problem. Are there any other questions on this example? Okay, let's look at the next example where we're comparing inductive effects. So chlorine are inductive electron withdrawing, and the greater number of inductive electron withdrawing groups, the larger our acidity. Because remember, these inductive withdrawing groups can stabilize our conjugate base anion. So in turn, this trichloroacetic acid would be the most acidic, followed by the dichloro, and finally the monochloro. The greater the number of inductive withdrawing groups, the more our conjugate base anion is stabilized, and as a result, the more acidic our parent acid will be. Does that make sense to everyone? Any questions? Okay, so let's keep going now, and let's arrange the following molecules in order of increasing acidity. So in terms of atom effects, larger atoms are more effectively able to stabilize a conjugate base anion's negative charge. So sulfur will be the most acidic, followed by the oxygen-hydrogen bond, followed by the nitrogen-hydrogen bond based on electronegativity, with the carbon-hydrogen bond being the least acidic. Does this example make sense? Perfect, perfect. So let's look at this next case where we have to rank the following molecules in order of increasing basicity. So in this first case, we have an sp3 hybridized nitrogen. In the second case, we have an sp2 hybridized nitrogen. In the third case, we have an sp2 hybridized nitrogen with a delocalized lone pair. So in general, the more localized and higher energy our lone pair, the more basic our nitrogen lone pair will be. Since the sp2 lone pair is the highest in energy and the most localized lone pair, this first compound will be our most basic. As such, our sp2 and localized lone pair will be our next most basic, followed by our sp2 delocalized lone pair, giving us the following ranking. Does this make sense?
Yep.
Perfect, perfect. So let's keep going now. In this case, we're asked to draw the products of each acid-base reaction using arrow pushing notation. Students need to really make sure to read the entirety of what I'm asking in each question, because that's where a lot of point deductions came into play. And it's really something that I'd like to see corrected before we get to later exams. You really want to make sure to read each question carefully and fully answer each portion of the question. So, showing arrow pushing notation, our base will attack our hydrogen, and then we'll break our oxygen-hydrogen bond to generate our anion. One other thing I noticed on the exam, you want to make sure that you're drawing your structures with clarity and precision. If the structures are not correct, I can't give points. Listing our pKa values, phenol has a pKa around 9.9, while this primary alcohol has a pKa of around 17. This exam was open book and open notes, so I was somewhat surprised that some of the pKa values were not assigned correctly. Additionally, please make sure to clearly indicate which compound you're labeling and referring to when you write a pKa value. This pKa refers to our parent acid, while this second pKa refers to the conjugate acid. Now, as we see, the phenol conjugate base is more stable than our parent alkoxide base, so this reaction would be product favored. Does this first example make sense? Does this first example make sense? Any questions on this first example?
Yeah.
Okay, so let's look at this next example now. So in this case, we are comparing acetone and the following diketone anion. So showing arrow pushing notation, we attack our carbon-hydrogen bond and we break our carbon-hydrogen bond. That in turn generates the following conjugate base and the following acid. This conjugate acid has a pKa of around 9, while our parent acid has a pKa of around 22. I noticed in some cases students mislabeled and mixed up the acid and base in this case. Additionally, please make sure your atom labels are reflective of the formal charges on each atom and the identity of each atom. I had some students end up writing something like this, which doesn't make any sense from the perspective of formal charges. Okay, so looking at our pKa, we see our product is more acidic. We also see that our reactant anion is more stable. This anion is overall more stable. So this reaction would be reactant favored. Does this example make sense? Does this example make sense?
Yeah, and just to clarify on the the arrow pushing, so we just draw to the proton that's going to be donating, and then you just show where it breaks.
Yep, exactly. And when you break your carbon-hydrogen bond, and the lone pair ends up on the carbon that was originally had that carbon-hydrogen bond.
Okay, got it.
Yep. And another example of this is also found in the review session recording as well.
Yeah.
Perfect. Does that make sense? And did that clarify?
Yeah, thank you.
Perfect. We'll be using this a lot more in later chapters when we start to draw more complex mechanisms. Okay, for question 5, we have to rank the molecules in order of increasing boiling point and note the major intermolecular forces. A lot of students skipped the second part and they lost points because of it. So again, make sure to read the question fully, answer every part to the question. So compound C primarily participates in hydrogen bonding. Same for compound D and compound A. Compound B has a polar bond and it primarily engages in dipole-dipole interactions, while E and F primarily engage in London dispersion interactions. Now, starting off, compound C has 2 alcohols, so it have the greatest number of hydrogen bonding interactions. So compound C would have the highest boiling point. Compound A is linear, while compound D is branched, and linear compounds in general have a higher boiling point than branched compounds. Hydrogen bonding is a stronger interaction than dipole-dipole, so all of our hydrogen bonding compounds would be higher boiling than our compound that exhibits dipole-dipole interactions. And dipole-dipole is stronger than London interactions, with our linear compound having a higher boiling point than our branched compound. So this is our final ranking. Does this make sense to everyone?
Yeah.
Perfect. Any questions that I can address? If not, let's keep going. In this case, we're asked to draw an orbital diagram, indicate the hybridization of each atom, and indicate the orbitals used for each sigma and pi bond. In many cases, the orbital pictures that were drawn were either incomplete or missing a lot of the labels needed. And then we have to assign formal charges to each atom. This oxygen has a positive formal charge. This oxygen and carbon are sp. This carbon's sp2. This oxygen is quote unquote sp2-like. And this carbon is sp3. So we've assigned the hybridization. Now let's go about drawing an orbital picture. So we have our carbon. So our first bond is going to be a sigma carbon sp3 plus carbon sp2. We also have a sigma carbon sp3 plus hydrogen 1s. In this case, we have a sigma carbon sp2 plus oxygen sp2. The lone pairs are held in sp2 orbitals. Then we have a sigma oxygen sp2 plus hydrogen 1s. Remember, this oxygen's sp2-like because it's conjugated. We have another sigma bond between a carbon sp2 and a carbon sp2 orbital. A lot of students miss that there's a hydrogen attached to this carbon, so you need to make sure to draw that. This is a sigma hydrogen 1s plus carbon sp2. Now to draw our pi bond, this would be a pi bond between a carbon 2p plus carbon 2p orbital. Remember, pi bonds are formed from the overlap of p orbitals. I noticed in some cases students labeled the pi bond as using hybrid orbitals, which is not correct. So we're up to here at this point. Next, we need to show our next sigma bond. And this is a sigma bond between a carbon sp2 and a carbon sp orbital. For our carbon-oxygen bond, it's a sigma bond between a carbon sp and oxygen sp orbital. And now we have to draw out our p orbitals. So for this carbon-carbon bond, even though there's not explicitly a pi bond in this case, this system is conjugated. I'll use a different color for that. And for our carbon-oxygen triple bond, we have two pi bonds. We have a pi bond from a carbon 2p plus oxygen 2p. And then we have a second perpendicular pi bond that is cross-conjugated. Only one of these p orbitals is conjugated with the other part of our pi system. Let me use a different color to show that. Additionally, looking at this oxygen, the lone pair on oxygen prefers to be held in a p orbital so that it can participate in conjugation and delocalization with the rest of our pi system. Finally, the oxygen lone pair would be held in an sp orbital. So this would be a complete orbital picture for the following molecule with all of the appropriate labels and appropriately assigned formal charges. Does this example make sense to everyone? Any questions on this example?
Not for me.
What was that? Oh, sorry.
Perfect. I was saying not for me. Yeah.
Okay, perfect. Any other questions I can address before we move on to the next example? Okay, let's keep going then. So question 7 looks trickier than it is. So we're looking at olefin hydration. And the first part of this question is to explain why cation 2 is generated preferentially over cation 3. I want to ask you to explain. You can use pictures if the pictures are completely comprehensive, but otherwise you may want to write a few sentences so that way it provides context to the pictures that you're drawing. So why is cation 2 generated preferentially? Cation number 2 is stabilized via conjugation with the adjacent pi system. And cation number 2 is stabilized and delocalized via resonance. So if we were to draw this with like an orbital picture, and use a different color pen for this. So we're able to delocalize and stabilize cation number 2 via delocalization throughout our pi system. So that's why cation 2 is generated preferentially over cation 3 under equilibrating conditions. Does this first part make sense?
Yep.
Perfect. So let's look at this next example where a reaction of cation 2 with water generates 3 unique products. So starting off, the reason why we generate 3 unique products is because we have 3 electron deficient carbons, and as a result, we have 3 sites of reactivity. So for example, water can attack at this first position. We can just as easily take our structure and look at another major resonance contributor. And in this structure, water can just as easily attack at our second electron deficient carbon. And finally, in our third resonance structure, water can attack at our third electron deficient carbon. So there are 3 electron deficient cationic carbons. Ergo, there are 3 sites of reactivity leading to 3 unique products. Does that make sense to everyone? How if you draw out the resonance structures, you can clearly identify the 3 electron deficient carbons, the 3 sites of reactivity, and as a result, that's why we see 3 regioisomers. Any questions on this example?
Nope.
Okay, so the last case, we're asked to provide a reasonable explanation for why alcohol number 4 is a minor product. Well, if we look at alcohol number 4, we see that alcohol number 4 has isolated pi bonds, which are less stable than the conjugated pi bonds observed in alcohol number 3 and 5. So essentially the fact that these double bonds are isolated rather than conjugated leads to a higher energy structure, and under equilibrating conditions, it would be easy to go back to the cation and then generate a more thermodynamically or kinetically stable product. Does this example make sense to everyone?
Can I ask a question?
Sure.
For this question, I had drawn a resonance structure without the alcohol, pointing out that number 4 was a 2', and whereas the other 2 weren't. And I was docked points on this one, even though I had written that it was less stable. And I guess I was wondering in the instruction.
Well, the argument that it's a secondary cation, ergo it's less stable, is not entirely comprehensive in this case, because you can make the same argument for why product 5 is minor because it's primary. By that logic, then you would think that product 5 would be even less likely to form. The reason why product 3 is major is partially as well because it's a tertiary carbocation, but it's not the effect of conjugation on the alkene stability and the stability of our final products is pretty substantial in this case, because all of our cations are delocalized and resonance stabilized cations. So the main deciding factor in our product distribution comes down not just to alkene substitution, but also the level of conjugation for the alkenes and the relative stability due to conjugation for each of our alkene products. So the secondary explanation, if you've made the argument that 4 is minor, well, a substitution-based argument would not be comprehensive enough to explain why 4 is minor compared to 5. Does that make sense? No problem, no problem. I wanted to make sure that my explanation was as comprehensive as possible. You can invoke carbocation substitutions, and yes, you are correct that a tertiary carbocation is typically more stable than a primary or secondary. That partially explains why product 3 is generated preferentially. But in terms of, in this case, when this reaction is run under equilibrating conditions, you also have to look at product stability in terms of factors like conjugation and substitution. And 5 is relatively more stable than product number 4 as a result of these conjugation effects. So there are a variety of explanations that would fully answer this question. You just want to make sure that, that your explanation is as complete as possible. Any other questions on this example? Okay, so let's keep going. So given the following formula and structure, we're asked to draw a series of constitutional isomers with the following criteria. So if we want a stronger carbon-carbon bond, let's just draw a triple bond. In this case, we have a du of 2, so we can have 2 double bonds or rings. That's a fair amount of flexibility, all things considered. Okay, so here's an example of a structure with a stronger carbon-carbon bond. If we want a structure with a proton with a pKa of less than 6, you can just simply draw a carboxylic acid. Let's just do the simplest case. It's not entirely correct because in solution, there's going to be a proton transfer, but this answer is perfectly acceptable in terms of the logic behind it. So the carboxylic acid proton has a pKa of around 4.7, roughly. So that's more than acceptable. The reason why this structure is not 100% comprehensive is that in solution, it'll pretty quickly undergo a proton transfer to generate a compound that looks like this. But this response would be more than okay to capture the idea behind this question, where you're asked to draw a structure that has a proton with pKa of less than 6. That's your typical carboxylic acid. Does that make sense?
Yeah, so you're saying this structure isn't as ideal because it's going to do a proton transfer upon itself?
Yep, exactly right. And then you'd end up with this protonated amine, and it's not quite as acidic as your normal carboxylic acid.
Oh, okay, gotcha.
Next, we're going to look at drawing a structure containing a nitrile functional group. So we want a carbon-nitrogen triple bond. Okay, 1, 2, 3, 4, 5. Okay, there we go. One thing that I noticed that was a little odd in some of these questions, students were drawing carbons with 5 things attached to them, which never happens. Make sure your structures obey the octet rule and formal charge rules, and that you place the correct number of hydrogens on each atom. Does that make sense to everyone? And does part C make sense to everyone? Okay, so continuing on now, we're next asked to draw a structure containing an amide. Okay, so let's do just that. Amide is the functional group that looks like this. One, two, three, four, five, and here we go. Here is a constitutional isomer that contains an amide functional group. Does part D make sense to everyone? Okay, let's look at this next case. We're asked to draw a structure with a higher boiling point, so we want more hydrogen bonding interactions. So we have the alcohol, the amine, and an alcohol. Some students drew the trans isomer, and in this case it's a little bit tricky because you have multiple bulky substituents, so it's not readily apparent whether the trans isomer would actually have a higher boiling point, because part of the reason why cis and trans isomers have different boiling points has to do with the stacking and packing efficiency and changes in the net molecular dipole. So I didn't accept the alternate alkene isomer because you really wanted your response to be a little bit more clear-cut and unambiguous. If you have a literature citation which demonstrates that the isomer that you've drawn has a higher boiling point, I would be willing to provide those points back. But I don't have any, it looks ambiguous to me whether the cis and trans, which isomer, cis or trans, would have the higher boiling point, just because of you have multiple polar substituents on each side of your alkene. This response with multiple hydrogen bonding groups is a little bit more clear cut, and this one would definitely have a higher boiling point. Does that make sense to everyone? Perfect. Okay, so let's look at the challenge question. So bridgehead amides have unique reactivities and properties. We're first asked to draw a major resonance structure for A. And would you expect this amide to be more or less basic? Okay, well, so drawing out our major resonance contributor. And I'm really surprised not many people made a model of this, because it's pretty obvious when you make a model that this structure is not very stable. So in general, following what's known as Brett's rule, bridgehead sp2 atoms are geometrically not allowed. It would introduce too much angular strain in your molecule. This does not exist. This is not This is not possible. You're not able to have a bridgehead sp2 nitrogen in this size of a ring. And because of that, since the bridgehead sp2 nitrogen is not permitted, resonance structure, the resonance structure for A is a negligible contributor. Thus, the lone pair on A is more localized and more basic. You can also make an orbital overlap argument. You can also make an orbital overlap argument that there is poor orbital overlap. And as a result, our lone pair is more localized. Sort of a backdoor argument using the same logic.
Can I ask another question?
Sure.
I had that on my paper and I only received 1 point. So I was wondering why.
I can look in detail, but usually let me rephrase. So in cases where not full credit was provided, there was either a logical flaw in the remainder of your argument that would either could not fully explain why A was more basic, or you provided a statement that was incorrect in your full explanation that required a deduction of points. So I remember that you did correctly argue from an orbital overlap perspective, but there were a few other statements in your argument that were not entirely correct and that ended up diminishing the argument's clarity. Does that make sense? So I gave points because the basic concept was present, but the full argument was not presented in a way that could fully explain why nitrogen A was more basic. And that's usually why I give partial points in this case. I was looking for at least some explanation of Brett's rule and the geometric constraints in order to explain why this resonance contributor was so minor for this bridgehead amide. Does that make sense? Did that clarify? If you have a specific question, I'd be happy to look over the exam and explain to you why I provided the number of points that I did. But just generally speaking, that's what I found in most explanations for this question, that usually when I provided 1 or 2 points, the argument had some reasonable points established, but it was missing other components that are needed for a full explanation. Does that make sense? But I'm not sure about the exact case that you're asking. And I'd be happy to take a look during office hours or after this recorded session. Did that address your question and concern? Perfect. And this was a pretty tricky question. I find if you made a model, it was a little bit easier to see. But overall, I was pretty happy about the number of students who were able to attempt and provide reasonable responses for this question, earning either full or partial credit. As this is an extra credit question, I also score it a little bit more strictly, as it is a little bit of extra credit on top of the exam. Beyond that, we're finished with the exam. It only took us It only took us about an hour to finish this exam if we were working diligently. One thing that I'd like to comment for submitting your exam for next time, if you could try to submit it as one PDF document, and if you could try to make sure that the images are as clear as and visible as possible, that would be really helpful in ensuring my annotations and my processing of your exams is a little bit more efficient. I made sure to grade all the exams in about a day's turnaround time, and I'm usually pretty fast getting the exams back since they're the most important indicator as a sort of a summative point in each semester. You'll be getting a grade update later on this week. And if you have any other questions on the exam or course content, really don't be shy to ask. I'd be happy to walk through any part of your exam. I just wanted us to do this exam review so that way we're clearing out this first portion of the semester's content and we're ready to move on. Because as you've noticed, we've already covered 2 chapters of content already, and we're looking to give the next exam once we finish chapter 5 and maybe chapter 6 if we're lucky. So just keep working on the material overall. For the students who attend these synchronous lecture sessions and meetings are doing really well so far, and just keep up the effort. We have the mentorship program tonight if you have any additional questions. And with that said, we'll close out today's recording.